Hello, good evening, what's up, and welcome back to another online tutorial for the 1001 MSc online tutorial series. My name is Brock Grant, and today we're going to be covering some calculations from some chemical equations, otherwise known as stoichiometry. So in this tutorial, we're going to cover two different things. We're going to be looking how stoichiometry is used in chemical equations, and we're also going to be covering limiting reactants and percent yield. So again, just a quick recap of what we covered in the last module, and the reason why I'm recapping it is because it is just so important. And that is that you must have memorized that 1 mole is the same as 6.02 times 10 to the power of 23 atoms. This is such an important number, it must be memorized. The next one is, what is the molar mass? So remembering that the molar mass is the mass in grams for 1 mole of a particular substance. So if we have carbon, so carbon on the periodic table has a molar mass of 12. Now, that means that if we had 1 mole of carbon, it would weigh exactly 12 grams. Now, this formula is one of the most important formulas that you will learn all semester. Okay, moles is equal to mass over molar mass. This must be memorized because in the next module that we're going to be covering, we're going to be looking at different versions of this formula based on whether we have a compound that is in a solution or not. And the last thing is that if we need to use a chemical equation or calculate something, that it must be a balanced equation. That is the first thing, is that we must have a balanced chemical equation. And secondly, if we're going to compare two different substances, we must compare their moles, not their mass. Okay, so let's look now more into stoichiometry. So stoichiometry is an area of chemistry that essentially focuses on the mathematical relationship between our reactants and our products. So the first thing we're going to look at now is how we can do calculations by using our molar ratios. So by molar ratios, it's essentially the ratio between how many moles of one compound or element versus another one. So we see here our question, so we can see how many moles of carbon dioxide will be produced by the complete reaction of 2 moles of glucose, according to the above reaction. So we have 2 moles of glucose. Now we can see here by our balanced equation that for every 1 molecule of glucose, it is going to make 6 molecules of carbon dioxide. So our ratio is 1:6, because for every 1 glucose molecule, it will produce 6 carbon dioxide. So it means that if we are given 2 moles of glucose, again, according to our ratio, it's going to make 12 moles of CO2. So this is how we can compare two substances by using their molar ratios. Now, the next one that we're going to look at is the calculations that involves moles and mass. So the question says, what mass of H2, so the molar mass has been provided here, is made by the reaction of 3 moles of hydrochloric acid with an excess of aluminium. So what the question is asking is it's asking us for the mass of H2. We don't know, but we do know that we have 3 moles of hydrochloric acid. Now we can calculate how many moles of hydrochloric acid will make how many moles of H2 by using our little molar ratios. So the best way to do this with any of these questions, and this is involving mass to mass comparisons, which we're going to do in a moment, is when you have the moles. So we know we have 3 moles of hydrochloric acid. And what I'm going to do is I'm going to take 3 moles and divide it by 6, which is the coefficient up here. So we have 3 moles of 6 hydrochloric acid. So we take our 3 moles and we divide it by 6, and this will give us 0.5 moles. Now, when we want to compare this molar concentration to H2, what we do is we can multiply this number by 3 because that is the coefficient that is at the front of our hydrogens. So 0.5 times 3 is 1.5 moles. So now that we have the concentration of 3H2, so we know the concentration is 1.5 moles, we can now use our moles mass molar mass equation. Now we know the moles because we calculated that as 1.5 is equal to the mass, which we don't know. That's what the question is asking for. So we're going to denote that as X over the molar mass. Now the molar mass has been provided for us here as 2.02. However, as you guys I'm sure are aware by now, we can also look up the molar mass on the periodic table. So we have 1.5 is equal to X divided by 2.02 grams per mole. Now again, when we rearrange this equation, it turns from a divide to a multiply. So it's going to be 2.02 times 1.5 mole. So that means that we are going to have a mass of 3 grams. And that is how much H2 will be produced. Okay, so now we're going to look at some calculations involving mass to mass. So the question is, what mass of bromide would be needed to completely consume 7 grams of aluminium? So how you would do this is that you need to convert aluminium to moles. Now that is extremely important because again, we cannot compare the masses of two different elements. You know, if we were to compare 5 kilos of bowling balls and 5 kilos of jelly beans, although they may have the same mass, we have a vastly different amount of jelly beans. You would have probably hundreds of jelly beans, whereas you'd only have maybe 1 bowling ball. This is why you need to convert it to moles, because it tells you how many of something you have of one and how many of the other, whereas you're not comparing it by mass. So the first step you would need to do with something like this is you would need to convert our aluminium here from its mass, which is provided, to its moles. And we do this by moles is equal to mass over molar mass. Once you have the moles, you then need to take into account the coefficient. So we can see here that we have a coefficient of 2 for aluminium and a coefficient of 3 for bromide. So that means with the molar concentration, it would be moles divided by 2, and then you would multiply it by 3 because of this coefficient. And that would then give you the moles of bromide. Then, once you have the moles of bromide, you can then use moles mass molar mass again and rearrange it so that you can find the mass of bromide. And that is how you can use stoichiometry to calculate our mass to mass calculations. Now, during a chemical reaction, the quantities that we use, so our reactants, are used up in a way so that one reactant is normally in excess. So it is very, very rare that we find that both reactants are used in a very equal amount to create a product. Now, the amount of product that is formed is often dependent on the limiting reactant. So the limiting reactant is the reactant that runs out first. Okay, so I'll show you an example now. So when you're doing your calculations on a chemical equation, it is the reactant that has the lowest molar concentration. So not mass, it is the lower molar concentration that is the limiting reactant. So for example here, if we have 4 car bodies, so this is a car, doors, engine, the lot, it just doesn't have any tires. So if we had 4 car bodies and we have 7 million tires, we've got plenty of tires. How many cars can we make? And the answer is 4. Because yes, we do have lots and lots and lots of tires, but if we run out of our car bodies, we can't continue making cars. So the maximum amount of cars that we can make is 4. And this is the limiting reactant, because it was the car bodies that ran out before the tires. So it means that our tires are in excess. And this is how this is the reason why we must convert the mass to the molar concentration so we can compare the numbers of one and the numbers to another to see which one will run out first. Okay, so now let us have a look at limiting reactants and our percent yield. So we can see here via the question, how many moles of ferric oxide can be obtained by reacting 16.8 grams of iron with 10 grams of water, and which substance is the limiting reactant? So we do this again by comparing the moles. We always convert it back to moles. So what we do is we go moles is equal to mass over molar mass. So the moles is equal to the mass of iron, which is 16.8, divided by the molar mass. So the molar mass for iron is 55.85. Now, we then just simply punch that into your calculator and we will get 0.3 moles. Now we do the exact same thing, but with water. Now, a lot of students fall into this trap where they just pause here and go, okay, we can see that iron has a lower concentration than water, so that means that iron is the limiting reactant. And to that I say be careful, because you need to take into account the coefficients. So 0.3 must be divided by 3, and 0.55 must be divided by 4, which means the molar concentration of iron is going to equal 0.1 moles, and the concentration of water is going to be 0.1375. So we'll round that to 1.4 moles. So in this case, water is going to be in excess and iron is going to be our limiting reactant, which means that when we want to calculate the moles of ferric oxide over here, it is going to be 0.1 moles. Now again, to calculate the mass of that, we simply use moles is equal to mass over molar mass. So we go 0.1 is equal to the mass, which we don't know, that's what we're trying to calculate, divided by the molar mass, which we can find out from the periodic table. So we add those together, and that will give us 231.55. So what we do again, we rearrange this formula. So I'll just write this over here. So it's going to be 231.55 times by 0.1 mole, which means the mass of this is going to equal 23.15 grams. Now, couple of things that we just did here. The first thing was we first calculated the limiting reactant by calculating the moles of each of these compounds and determining which one was the lowest molar concentration. The next thing we did is we calculated what is called the theoretical yield. So this is how much product can be formed, assuming that every single atom of the reactants is being used. So by doing it this way, we calculated that we had 23.15 grams of Fe3O4 created from 16.8 grams of iron and 10 grams of water. Now we need to compare theoretical and actual yield, because throughout basically all of these videos thus far, whenever we've done any sort of calculation in a reaction involving calculating how much product will be formed or anything like that, we have been calculating the theoretical yield. Now, theoretical yield is essentially how much product can be formed, assuming that 100% of our reactants are going to react together to form the products. Now, unfortunately, in real life, things are not that simple, and 100% of the atoms in our reactants do not react together, okay? So the theoretical yield is how many is absolutely possible, the absolute maximum amount of product that we can form. However, we also have what is called the actual yield. Now, our actual yield is how much we actually get. And this number is deduced by doing actual experiments and figuring out, normally by mass, how much of a product that was made. So this equation absolutely must be memorized. You must know this. So the percent yield is equal to the actual yield divided by the theoretical yield times by 100%. So what the percent yield tells us, it tells us how close did we get to that theoretical yield. So the theoretical yield is the absolute maximum that can be made, no ifs, buts, or maybes. It's if we get 100% of all of our atoms to react together and form the absolute maximum possible product. So that is our theoretical yield. The actual yield cannot be calculated. Okay, it must be done in practice. We must actually go into the lab, do the experiment, and determine how much product was formed. So these two combined will give us what is called the percent yield. So that tells us how close did we get to achieving our maximum results. So for example, if we had a percent yield of 50%, it means that we only made 50% of the product that is theoretically possible. So for example, carbon tetrachloride was prepared by reacting 100 grams of carbon disulfide and 100 grams of chlorine. Calculate the percent yield if 65 grams of CCl4 was obtained from the reaction. So what this means is that we are given the mass of carbon disulfide. We are also given the mass of chloride. So what we do then is we calculate the moles of each of these and find out which one is the limiting reactant. Once we've found out which one is the limiting reactant, we then use that concentration, and we can use that to tell us the molar concentration of carbon tetrachloride. We can then use the molar concentration of CCl4 to convert that into the mass of carbon tetrachloride. Now, remembering what I said to you guys before when we were doing the previous question, is that the mass that we calculate via this method here, that is the theoretical yield. So what we can then do, we can feed that theoretical yield into this part here. Now, the question also said, now this is where the question can be a little bit tricky. It said if 65 grams of carbon tetrachloride was obtained from this reaction. Okay, so a lot of people may fall into the trap of going, oh, well, I already have the mass of carbon tetrachloride, so what do I do here? This mass here is the actual yield. So that someone went into the lab, they did this experiment, and they found that we got 65 grams of carbon tetrachloride. So this one here would be 65 grams, and the theoretical yield is this number that we would have calculated by doing this method. So then we divide one by the other and we multiply it by 100, and that will give us our overall percent yield. So again, it is this type of question where students can often fall into the trap of going, oh, I don't need to calculate the mass of our product here because it's already been given to us. And that's the trap, because as we can see here, we have two different types of yield. So again, we have our theoretical and actual yield. So these are the step-by-step instructions that you need to do to solve any and all percent yield problems. Is that we need, again, it all comes down to reading the question very carefully. That is the most important thing with all of stoichiometry and basically any exam that you're going to sit. And that is, make sure you read and understand what the question is giving you and what the question wants you to answer. Because as I showed you before in that maths question, it's very easy to get them confused. You then write down your equation and determine what you need to calculate. So if you do need to calculate the theoretical yield, you do it in this manner. Now, again, you need to find the limiting reactant. If you do not find which one is the limiting reactant, you have a 50% chance of getting it wrong. Okay? And that's assuming you only have 2 reactants. So make sure you always calculate the limiting reactant. Once you have the limiting reactant, you can then move on to calculate your percent yield via this formula here, which absolutely must be memorized. Absolutely must be memorized. Now, I'm going to give you a bit of a tale of caution because, as I've said to you guys previously, I have my top 3 student killers. Acids and bases, which you guys aren't going to do yet. Redox, which was our previous module, which I'm sure a lot of you probably did find a bit difficult. And stoichiometry. And this is why this part is so difficult. Because it's so easy to make very silly mistakes. As we're going to cover in our next module, we're also going to look at not only moles, but molarity and molality. And then we're going to look at mass percent, volume percent. This is where it gets very, very confusing to identify what is what. And again, what these numbers are trying to tell you. Okay? So it's very easy to lose marks based on silly mistakes, based on not understanding the underlying theory or concepts of this module, or to just simply jump steps, to not realize, like for example, to forget to calculate the limiting reactant. It's little things like this that cost students dearly, very dearly in exams. So again, when you're in a chemistry exam, make sure that you always read the question carefully. So put your pen down, read the question, then pick your pen up and then read the question again. And I want you to underline, circle, bracket, whatever you like, what the question wants from you. So ask yourself, what does the question want? So what does it want you to answer? Now, the next thing too is have a plan. Find out what the connection, what is the link between what the question gave you and what the question wants. Because a lot of the times it may just look like that the question is just giving you a heap of these random numbers that doesn't have any meaning, when in actual fact, there is only one link between all of those numbers, and it tells you what equations you need to know. Another thing too is make sure you have all of your formulas and all of the key information memorized. My 4th tip is make sure that you don't just memorize the content, especially in chemistry. You must understand the content, okay? It is very easy for us in an exam situation to change the number, to change the element, to change the coefficient, and completely produce a brand new question. So it's pointless in trying to memorize your questions because we're just going to change them. But if you understand how to solve the question, it doesn't matter what we give you. We can give you the most complicated chemistry questions in the world. It will still be a piece of cake because you will know exactly what you have to do. So thank you very much for joining me for Module 8 Video 1. If you could all just please complete the survey down below, it really helps me out a lot and allows me to continue making these videos for you and allows me to improve them and make them better. If you do have any questions, queries, suggestions, please feel free to email me at b.grant@griffith.edu.au. Keep up the hard work, guys. Thank you very much for joining me today, and I'll see you next time.